Okay, so good morning, everyone, and thank you for joining us today. So my name is Alessandra Cuneo, head of the Power Generation and Hydrogen R&D in RINA. I am a senior environmental engineering specialized in power generation, hydrogen technologies, and innovation management. And on the behalf of the Clean Hydrogen Partnership and SoftWater and Fondación de Aragon that carry out these studies, I would like to warmly welcome you today to today's webinar, which is dedicated to the sustainability of water use and management in renewable hydrogen production. So next slide. So this is just, let's say, to give you before the context, the renewable hydrogen, as you know, is expected to play a crucial role in the Europe decarbonization strategy. But as you know, while hydrogen is increasing a part of the solution to the climate change, one important question is receiving more and more attention in the community. That is how we can scale renewable hydrogen without creating new pressure on water resource, because water is not only an input to electrolyzers, but it's also linked to the energy production, to the cooling system, to the local ecosystem. So understanding this relation between the hydrogen production and the water availability is more and more important. And it's essential to understand that if we want that hydrogen deployment be a climate smart and water smart solution. So I'm delighted to, let's say, moderate this webinar today. And over the next 1 hour and a half, more or less, we will share the results of this comprehensive study that has been commissioned by the Clean Hydrogen Partnership, which have the aim to exploring the interaction between hydrogen deployment, water availability, and climate resilience across Europe. So the first of all, we'll present, let's say, we will have opening remarks from Mirela Taniasus from the Clean Hydrogen Partnership, Luigi Crema from Hydrogen Europe Research, and myself as well to present a little bit more in detail the objective of the study. Then we will first present the main findings of the study, which include the regional assessment, the modeling activities, and the case study analysis we perform during this year of work. And then we will move into a panel session in which experts from the policy, the industry, and the research organization explore how these fundings can support future hydrogen deployment strategy. Two aspects. So we will have an audience question and answer session between the first session on the results and the second section as panel discussion. And I would like also to highlight that the results that we will present today is just a part of the study. So we included the main results achieved to give you a flavor and overview of the key takeaways of the study as well. However, a deeper and longer and detailed summary of the study will be published on the Clean Hydrogen Partnership webpage in the next months. So next slide. So before, let's say, moving to the first speaker, just some rules of the webinar. So all attendees have the muted microphone by default, and question could be addressed by the question and day tab, and we will address it and answer during the dedicated session. The webinar will be recorded and will be published on the Clean Hydrogen channel on YouTube, and the presentation that you will see today will be made public as well on the Clean Hydrogen Partnership webpage. So to officially open today's webinar, it's now my pleasure to give the floor to our first speaker, Mirela Taniasus, is the head of Unit of Operation and Communication of the Clean Hydrogen Partnership since 2016, which is a public-private partnership between European Commission, European industry, and research community. So Mirela, thank you very much for joining us, and the floor is yours.
Good morning everybody here in Europe, and let's say good afternoon if you follow us from other parts of the world. Really pleased to be here with you and to reach this milestone, to be able to show to you the results of this one-year study. Thank you very much, Alessandra, for the nice introduction. Yes, like I said, my pleasure to be here and to be able to open this hopefully very fruitful webinar with a lot of insights from the work over the past year. Before we get into the content and not necessarily knowing very well the audience, I took the liberty of preparing just 2-3 slides in case the audience do not know the partnership and what we do in Europe or what we have done in Europe. Just 2-3 slides to introduce you to the partnership, so that I set up a bit the background. So if we go to the next slide, I will just tell you that for those that do not know us, we exist for more than 18 years. We have been created in 2008 by the European Commission when the European Commission, the EU, the European Union has decided to speed up the implementation of innovation, research and innovation activities in Europe, and how to do that better than in a partnership with both the industry and the research community. The industry and research community who have themselves organized in 2 main associations, Hydrogen Europe and Hydrogen Europe Research, and counting altogether more than 750 members. So this is the most powerful instrument that European Union has when we talk about innovation at EU level. And I think over the last 18 years, we have proven that working in such a partnership and bringing all the actors around the table, we have achieved important results. One of them being even the study that we present today, for example, in which we do not only address scientific or innovation matters, but we also answer to policy matters. For this life of the partnership, for this financial framework, for this current 7 years at EU level, we have €1 billion from the Horizon Europe program to implement such activities and to continue to innovate, decrease the cost of the technology and improve the performance of the technology, while, like I said, also supporting policy and industry and research community. In addition, we have also received through the Repower communication of the Commission when Russia invaded Ukraine, we have received 200 million in recognition of hydrogen valleys as being one of the most innovative business model to speed up the hydrogen projects. In recognition of that, received additional budget to implement it between 2023 and 2025 in a 3 years window, to speed up, like I said, the projects on the ground in an ecosystem approach as the valleys. Now, if we go into the next slide without getting into the detail, and in case you are wondering what do we do with the billion, we spend it in different technologies across the entire value chain or supply chain of the sector, from the production technologies, mostly electrolysis and only renewable hydrogen production, up to the distribution storage, going from all types of storage, above ground, underground, different carriers, compressed liquid hydrogen, ammonia, pipelines, all types of pipelines, and of course all the technologies around that, compression, purification, metering, and then up to the end users, both on the transport side, but also on the heat and power and industrial solutions, for example, for use of hydrogen, going from the heavy duty transportation solutions, for example, up to the use for heat and power in turbines, in boilers, in stationary fuel cells, or even using hydrogen as a feedstock, for example, in hard-to-abate industries. And of course, we do many activities also of a cross-cutting nature, such as safety, pre-normative research, education, with the first of a kind hydrogen academy in the world. We also look at supply chain matters, such as reducing the dependence on critical raw materials from outside Europe, or we innovate at business model, like I just said, with the hydrogen valleys concepts. In the next slide, I'm just illustrating what I just said, and telling you that this was always for more than 17 years, 18 years recently. We have innovated in a feedback loop approach. We always go from the lab. We build products through a series of projects, and so far we have supported more than 400 projects for now counting 2 billion support over the last 18 years, like I said. We go, we validate into the field, we learn, we demonstrate across Europe, and we go back into the lab. And in this way, for some products, we have gone through 4 or 5 generations of products, for example, and we have, like I said, improved performance, durability, and decreased the cost. And one of my last slides, next, it's my pitch on competitiveness. Of course, in doing that, we contribute to the competitiveness of our industry, of our sector, because, like I said from the beginning, we bring all the actors together. We do not work in silos. We bring industry with research, with academia, with policymakers, but ultimately with member states, with countries, with regions, and all the necessary actors, including civil society, for example, when we talk about projects on the ground. And we do not only do that, but we are also with our tools for knowledge monitoring. We monitor how we progress on that. And I will here just mention, for those that are curious, to just Google Hydrogen Observatory and you will see what I'm talking about. Next slide. And I think it's my last. It is a moment now that with the next multi-financial framework for the next 7 years at EU level, where we need we need help somehow, because we are convinced, as you can see me talking, of course, we are convinced about what we have reached, but I think you have also the opportunity, you, the audience here, and I take this opportunity to remind you to also say, eventually, if you resonate with anything that I'm saying right now, to also say that again to the policymakers and to recognize what we have done. And I would kindly encourage you to answer to this call for evidence, which the European Commission has published on the 16th of June. The deadline is next week. And I think it's an opportunity to say again to the Commission how to shape the future for the next 7 years, and how Europe should stay in the lead through innovation and in working in a partnership. Now, before we go to the next speaker, I would like to go to I finished with the introduction, and I would like to thank you very much for letting me do that and get a bit address the audience on more general terms and what partnership has done for the last 18 years and what it can still do and where it can still offer impact. But now coming to the point of today's, and I will make the link to what I just said before. We know that due to the partnership by 2020 and what we have delivered, the European Commission has put in place a hydrogen strategy in 2020 and has raised its ambitions, in particular with the Repower EU in 2022, has put a plan and a target of producing 10 million tons of hydrogen in Europe and importing other 10 million of tons. With this raising hydrogen production volumes, the question, of course, immediately came on the water and the water stress, in particular in Europe. As we know, the climate change impacts water availability. We have areas, zones in Europe with a lot of stress and scarcity of water. And that's why, again, as a partnership and talking together with all our members, with all our partners, we agreed in 2025 last year to put in place a study and to look at if we really have a problem, and if we do have a problem, what's the problem? When we talk about water scarcity, water availability of water, or water sustainability. How much, for example, water the hydrogen production needs? Is this really impacting the stress of the water stress and the impact it impacts also like the climate change is doing? And in doing that, our colleagues in RINA here have helped us, and they will present in a moment the preliminary and final results. And we have also looked at 5 different case studies, trying to show and to answer to these questions that I just mentioned, either by showing the local impact of hydrogen projects, for example, in areas which are already experiencing drought, such as Spain or Greece, or in areas which are relevant for the entire Europe geography, such as Croatia, Slovakia, or France. So this will be the 5 case studies that we selected to look at and to see if we really have a problem. And we will also see that the water stress and the water availability, it's a side-dependent variable, of course. And what matters is not only the processed water, but also the quality, the treatment, the cooling. So we need water not only in producing hydrogen, but we need water across the entire processes of when we talk about hydrogen projects. And of course, we have solutions. And in the same time, the partnership that my organization has already started working on, for example, producing hydrogen from seawater or from dirty wastewater, has also looked at recycling of water and trying to show that we can ultimately develop hydrogen projects everywhere across Europe. Finally, all these findings and all the data that have been captured through the different studies will be today launched together in a Clean Hydrogen Explorer platform that we will have the pleasure to launch today, developed, of course, by our colleagues, contractors in RINA. And later we will also, and follow us, follow our website, we will publish the final report like Alexandra already mentioned at the beginning. And I would like to finish by just thanking everybody. Thanking first the contractors, Alessandra, the team in RINA, thanking our members always, and thank you, Luigi, for being with us today, representing my board. Thanking colleagues in the Joint Research Center who are always with us, checking on sustainability matters, including those of water. Thanking our invitees who have joined us from all different organizations to look at the matters. And last but not least, thanking my team here today, Luca Feola, who's the project officer in charge of these matters in my team. And last but not least, my communication team, who's behind. You don't see them, but they have helped enormously with everything that happens today, and not only. So thank you very much, and I wish you a fruitful webinar. Really looking forward, even myself, to see the results. Thank you. Alessandra, back to you.
Thank you very much, Mirela, to you and the Clean Hydrogen Partnership as a whole. And I'm pleased now to introduce our next speaker, Luigi Crema, which is the director of the Center for Sustainable Energy at Fondazione Bruno Kreisler. and he serves also as president of Hydrogen Europe Research, a member of the governing board of the Clean Hydrogen Partnership, contributing to the definition of European hydrogen research and innovation priorities. And he is also vice president of the Italian Hydrogen Association. So Luigi, thank you for being with us today, and the floor is yours.
Thank you, Alessandra, and good morning, everyone. I'm thankful for the kind invitation to this interesting webinar, which is one of the important topics for the future scaling up of the hydrogen sector, indeed. It is a pleasure to be here today on behalf of Hydrogen Europe Research. Hydrogen Europe Research brings together around 180 universities, research centers, and innovation organizations across Europe and even beyond, involving even members from Canada and New Zealand. As the research pillar of the European hydrogen ecosystem and partner, as said by Mirella, of the Clean Hydrogen Partnership, our mission is to develop knowledge, technologies, and skills that could and will make hydrogen a cornerstone of Europe's energy transition, of the industrial competitiveness and energy security, as well as of main topic today, even environmental sustainability. We are looking for new research priorities, future research priorities that could support the present and future programs of the Clean Hydrogen Partnership. For such, we are organized in 4 working groups supporting low TRL research, so what should come next, then the role of research and technology infrastructures in Europe to accelerate the deployment of technologies and leverage the impact of innovation, then developing skills and competencies in Europe through the Skills Task Force, and finally, we are supporting policy development in Europe. Today, I would like to focus on a simple question regarding the topic of the webinar. Can Europe scale renewable hydrogen without putting additional pressure on water resources? My answer today is optimistic and positive, so I would say yes, but only if research and innovation remain at the center of hydrogen deployment. First, I think it is important to put this discussion into perspective. Hydrogen production does require water, there is no doubt about that. But if we compare electrolysis with agriculture, conventional power generation, or many industrial processes, the amount of water directly consumed is, at least today, relatively modest. So the real question is not simply how much water hydrogen uses. The real questions are which water, where, under which local conditions, and how can we use it more intelligently, of course, in a perspective of scaling up the sector globally and in Europe. So looking to a progressively increasing water utilization in the future for hydrogen production. This is exactly where research can make the difference. From the perspective of Hydrogen Europe Research, I see 5 major research priorities. The first is broadening the range of water sources. Fresh water should not always be the default option. We need technologies capable of using treated wastewater, industrial process water, desalinated seawater, and in the future, even direct seawater, wherever technically and economically viable. And Mirella already mentioned that the Clean Hydrogen Partnership is supporting research in this direction. There are several initiatives that are today supported, developing technologies for seawater and even gray water use. The second priority is improving electrolysis technologies themselves. So future electrolyzers should become more tolerant to different water qualities, requiring less purification, consuming less water through better system design, and achieve even higher efficiencies. The third priority is thinking beyond the electrolyzer. Water should not be considered as input that is simply consumed. It should become part of a circular industrial ecosystem where it is recovered, it is recycled and reused through the hydrogen production processes. The fourth priority I see is digitalization, artificial intelligence, digital twins, and predictive control can optimize hydrogen production together with water management, adapting plant operation to renewable electricity availability and even local water constraints. And finally, the fifth priority is integrated territorial planning. Hydrogen deployment cannot follow a one-size-fits-all approach. Every region, as said by Mirella, has different renewable sources, different industrial demand, different water availability. We need integrated planning tools that optimize all these dimensions together. This is exactly why hydrogen valleys are so important. They are not only demonstration projects, they are real laboratories where we can validate integrated solutions under real operating conditions. So let me conclude with the same question I started with. Is water a challenge? Absolutely. Is it a barrier? I don't believe so. I believe water sustainability is one of the great innovation opportunities for the European hydrogen community. If we invest in smarter electrolyzers, alternative water sources, circular water management, digital technologies, and integrated territorial planning, we will not simply produce renewable hydrogen. We will produce better hydrogen, hydrogen that is not only climate neutral, but also resource efficient, resilient, and truly sustainable. And this is exactly the contribution that European research is committed to delivering. So thank you very much for the kind invitation, and I wish you and all the presenters a very nice, interesting sharing of information for the study and the discussion in the forthcoming panel. Thank you, and I leave the floor back to Alessandra.
Thank you very much to you, Luigi. So let's say your remarks and your speech highlight the importance of also linking technology innovation with the real world deployment. So I'm glad to start to present you the objective of this Clean Hydrogen Partnership study. And so in the next slide, before discussing the results, let me start with the simple question that is posed by us during the study. So can renewable hydrogen scale in line with the requirement European decarbonization targets without compromising the water resource? So this question was the starting point of our study. And you know that hydrogen is widely recognized as a key enabler of the energy transition, however, required a lot of water consumption, not only in the through electrolysis itself and electrochemical process itself, but also additional water is needed for the full system perspective. So for the treatment system, for the cooling system, and all the upstream activities associated with the energy supply. So another, let's say, aspect that was discussed during the study is that water risk is inherently local. So at European scale, projected water demand from renewable hydrogen appears manageable. However, the local and the seasonal pressure that can emerge when hydrogen deployment overlap with water scarcity, drought condition, or competition with the other sector present at local base. So the hydrogen planning must integrate water availability, must integrate siting decision, must integrate climate resilience and social acceptance from the early stage of the project deployment. So in the next slide, we summarize which are the main objective of the study that was to assess whether the expected scale-up of renewable hydrogen can remain compatible with the sustainable water use. To achieve this goal, we pursued several complementary objectives. First of all, we quantified which are the water requirements associated with renewable hydrogen production. Secondly, we investigate which are the future water needs under the different hydrogen deployment and climate scenarios, so seeking to understand where future pressure may emerge. And third, we assessed the feasibility of alternative water sources, such as treated wastewater, brackish water, seawater, and we will go through this both during our result presentation, but also during the panel session, that of course can reduce the pressure on the freshwater resources in a vulnerable region. And finally, we explored which are the policy implications to identify also practical recommendation for sustainable hydrogen deployment, particularly in water-stressed region. So the study was designed to provide policymakers, project developers, regional stakeholders with some evidence-based guidance that can ensure hydrogen expansion support climate goals without creating an unintended pressure on water resources. So I will not go through much in detail in the methodologies that we presented in the next slide. So the study was divided in four main tasks, which more or less are aligned with the project objective that I described before. So at the end, the outcome is a comprehensive assessment of the water, energy, hydrogen nexus. So I will not go into detail because I think it's really interesting to go into details in the results that we achieved during the study. And one of these measure output of the project, as anticipated before also by Mirela, is the Clean Hydrogen Explorer, which is an interactive platform designed to support policymakers, developers, and researchers in understanding water and hydrogen interaction at different scales. So to present this tool, I'm delighted to invite Marco Micotti from SoftWater. He's one of the co-founders of SoftWater. He's an environmental and land engineering. He has more than 20 years of experience supporting public and private organizations in environmental monitoring, management across local, regional, and international context. So, Marco, the floor is yours to officially launch and present the Clean Hydrogen Explorer platform.
Thanks, Alessandra, and good morning, everyone. Thanks for the introduction. Our main role in this study as a SoftWater was to support the analysis with data coming from, let's say, scientific-based analysis, simulation, and tools. So the main outcomes, let's say, the main visible outcomes of this effort is the Clean Hydrogen Explorer. Next. Which is a data visual analytics web tool, and we also want to stress it, which is that is a data-driven platform in the sense that while we speak and think as presented in the opening remarks, which are the best conditions for clean hydrogen development in terms of water availability and energy, renewable energy realization and production, we need, let's say, to deal with very distributed data set and information that change in time. And so what we did was to analyze this nexus among water, energy, and hydrogen at two different scales. One at the pan-European, let's say, in the pan-European context, using the regional scale as a, say, spatial unit. And then we went deeper at the single case study, using a 5 case study of different regions across this pan-European area in order to go much in more detail and see the real effect of introducing hydrogen in a context where water is also used for many other uses and from many other actors. So this one that we see here is the landing page of our Clean Hydrogen Explorer, and behind, let's say, the data that we will see in a while, there is a processing pipeline, next, which for the regional analysis is composed by 5 steps. The first is data ingestion. So we collected several European and global scale data set dealing with both methodological and energy production or hydrogen development plans data set. We pre-process them and harmonizing them and aggregating at the same spatial level of regional level, and then we compute indexes that told us the situation in terms of water availability, renewable energy production, and the hydrogen development plans in each specific region. These indexes, as well as input data, have been then organized in a visual in a database and in a number of visualization combined then in a web interface, which is the Clean Hydrogen Explorer that we are presenting right now. Next. The 2 sections are, let's say, can be accessed from the top menu bar in this platform, and we have for each component of the nexus, water, energy, hydrogen, dedicated page where each page is, let's say, is described in detail in a specified section, and the data that are present in each section can be browsed and inspected using both temporal or index value based filters on the top on the visualization. In this page, which is related to the water component, what we see here is the representation for the historical period, so covering 20 years from 2000 up to 2020 of distributed water availability indexes, so the water exploitation plus index, the aridity index, and 2 elaboration of the standard precipitation index at 12 months. Next. For what concerns hydrogen, we included in our platform the plans for development of hydrogen production in the entire case study area, and then we aggregated them at the regional scale, maintaining also the information of the localization of each single plant. By clicking on a region, then a regional dashboard page can be also accessed, where yearly time series of indexes can be evaluated, because very often in this kind of study, what is done is to consider the average behavior of a system, of a region, of a case study in the historical condition. But what we think is relevant is to understand when the system is under stress under which specific conditions. So it's important also the temporal distribution of the indexes, as we can see here in the regional dashboard page. To combine all this information, a few analysis pages are also available. The one that is presented here is a cluster analysis, which basically is targeted to identify potential suitability of different regions to host future clean hydrogen development. We have different clusters have different colors in this visualization. For instance, we have filtered all the regions that have a high and medium high suitability to host hydrogen development, and what we see is that for many of the regions where hydrogen development that are suitable, so can let's say support both in terms of water and energy, renewable energy production, hydrogen development. We have already some hydrogen plants, which are the dots in the map, but all these dots are pretty small, so it means that there are limited, let's say, expansion planned, while the bigger dots are representing higher plants with a higher capacity, higher target capacity. So in this same visualization is also telling us that, for instance, the orange areas which are, let's say, representing the medium-high cluster, so which are still potentially interesting for development of hydrogen, have less or no plans for development. So this can be a useful tool to inspect region by region, or let's say macro region at a macro region scale, where are the hotspot of interesting availability or suitability for hydrogen, clean hydrogen development. Next. As anticipated, we also run a more detailed simulation on 5 case studies, developing, let's say, a top-down framework which is widely used for climate analysis. And so basically what we did is to use the climate projection, which are valid at a global regional scale, but we downscaled with a statistical method to adapt to the local context of each case study selected. And then we run hydrological simulation to evaluate, let's say, condition of the specific case studies with the introduction of, let's say, the water use by hydrogen. And the results of this simulation has been translated into impact indicators. All this process has been also documented in the platform. Next. So we have a section which is a case study, which present for each one of the 5 case studies the results, both in terms of, let's say, plant localization, river catchment considered for the hydrological simulation, and plant technical specification information, but also presenting those impact indicators that I mentioned before. Like in this case, we see on the top right panel, we see surface water availability as resulted by, let's say, given by the hydrological simulation, and its distribution across the 4 seasons, which are represented with different colors. So this level of details is also available in the platform for each case study. And I think that I can now leave the floor to Gianluca, which is, let's say, our partner that took in charge more in detail the case study analysis.
Yes,
thank you, Marco. Sorry.
Yeah, thank you, Marco. And let's say, as anticipated, to present the results of the case studies, I would like to welcome Gianluca Greco, which is a chemical engineering and as head of the consulting department at Fondazione Aragon. So the floor is yours, Gianluca, and I kindly ask you to, let's say, short a little bit the presentation since we are a little bit behind the schedule. Thank you so much.
Thank you, Alessandra. Thank you, Marco, for the presentation. Hello, everyone. Thank you for joining us today. I will try to be very, very brief in presenting the main insights obtained from the assessment of the 5 case studies that we selected for the study, and based on the 5 European hydrogen valleys, focusing on the relationship between the water resources and the renewable hydrogen production. Beyond the modeling results, this work also incorporates feedback from project stakeholders, providing practical perspectives on how different regional conditions affect the water management strategies for the hydrogen deployment. And after introducing the assessment framework, the next step was to apply to 5 representative hydrogen valleys across Europe, And each case study represents a different water context, allowing us to compare how regional conditions influence the interaction between water resources and the renewable hydrogen production. And as you'll see in the following slides, despite all projects pursue the same objective, the water-related challenges are, I would say, remarkably different. Next slide, please. Okay, it is important to highlight that these hydrogen valleys are very different from each other. And as it is shown in this table, they differ in terms of electrolyzer technology, project maturity, production capacity, electricity source, water abstraction, and water supply. And these project-specific characteristics, they were incorporated into the assessment, allowing each hydrogen valley to be evaluated according to its own technical and operational conditions. Next slide. Okay, so once the project-specific characteristics were incorporated into the assessment, a common set of indicators was generated for each hydrogen valley using the same modeling framework. And the figures presented here summarizes the two key indicators used within the evaluation. As you see here on the left, the number of days in which the sulfur water availability is enough to fully meet the projected hydrogen-related water demand. And on the right, the amount of hydrogen production that can be supported by the available surface water under historical and future climate scenarios. And these indicators provide a consistent basis for evaluating how different regional conditions may influence the water availability for hydrogen production. And they also formed the basis for the subsequent assessment of seasonal water deficits and the development of the case-specific water management recommendations presented in the study. Next slide, Alessandra. Using the indicators generated by the assessment, we identified a number of common patterns across the 5 hydrogen valleys. And despite the same methodology was applied to the 5 case studies, the results highlight different regional responses under the analyzed conditions. Within the case studies analyzed, the Mediterranean hydrogen valleys, particularly the Green Island and the Pira project, show the stronger influence of seasonal water variability, with watering constraints becoming more pronounced during the summer months. And in contrast, the continental case studies generally exhibited more stable hydrological conditions, where the water availability is less likely to limit the hydrogen deployment under the analyzed scenarios. And these findings demonstrate that the regional context plays a key role in defining both potential water-related risks and the most appropriate resilience strategies, reinforcing let's say the need for case-specific water management approaches. Next slide. To complement the modeling results, we discussed the findings with representatives from each hydrogen valley. Of course, every project confirmed that the water management is an important consideration, but the discussions show that the priorities differ significantly across the regions. Indeed, in the Mediterranean projects, they focused on issues such as the tourism, the biodiversity protection, and alternative water sources, while the continental projects emphasized the climate resilience, the water quality, economic viability, and the early project planning. So the main lesson is that there is no one-size-fits-all solution. The water management strategies must be adapted to local environmental, technical, and socio-economic conditions. And successful hydrogen deployment requires integrating water management with environmental protection, economic viability, project planning, territorial conditions, local regulations, and so on. Next slide. Just to conclude, our work shows that the water availability should be considered as a strategic component of renewable hydrogen deployment, but always within its local context. So the combination of regional assessments and the stakeholder consultations provides a more complete understanding of the opportunities and the challenges faced by the hydrogen valleys across Europe. And finally, there is, as I said before, there is no universal solution. Instead, resilient hydrogen deployment depends on selecting water management strategies that are technically feasible, environmentally sustainable, and adapted to, as I said before, to regional conditions. So to conclude, the water may not be the largest resource required for renewable hydrogen, but understanding its regional context is essential for building resilient hydrogen-based projects. Thank you very much.
Thank you very much, Gianluca, for the presentation. And I remember that if you have any question, you can use the Q&A section to provide question to the speaker, and we will briefly answer you during the next session. But before moving to the Q&A, I would like to conclude this technical session by summarizing which are the key lessons, the key takeaways, learning, and discussing also what they mean for the future water smart hydrogen deployment. So the first results and the most important finding of the study is that the water footprint of hydrogen production is much more complex, and it's really complex. And our analysis showed that while direct electrolyzer consumption is relatively similar across technologies, the total water impacts strongly depend on the treatment processes, the water resource, and the cooling configuration. In the slide, we included the main results related to the water consumption and withdrawal when we use tap water as sources. In any case, in the summary of study, we performed the same analysis also for the seawater and the surface brackish water, and the hydrogen production treatment costs based on the source, water source, and from the different hydrogen technologies. So just summarizing what we have seen related to this water footprint analysis is that seawater, for example, can provide an abundant resource in the coastal region, but require, of course, more intensive treatment and generates additional brine management challenge. Of course, while brackish water often represent and could represent a useful compromise. And the treated wastewater, which was one of other water resources that has been studied, can offer a highly attractive circular solution when and where suitable infrastructure are available in the local context. Cooling systems are equally important. Evaporating cooling typically increase, of course, water consumption, and dry cooling minimize which are the water use, but may introduce efficiency penalties on the system level. So the key message related to water footprint is that, as mentioned, let's say from the beginning, looking only at processed water consumption risk underestimate the true pressure on the local water resource. The main key takeaways related to the water demand and capacity projection. In the next slides, from our regional analysis, we examine the future hydro deployment that may evolve in Europe and in neighboring region. And the results show a substantial growth in hydrogen production capacity, particularly in the Mediterranean area and in North Africa. And at macro-regional scales, also the associated water demand remains relatively limited compared with the total water withdrawals, also considering which are, of course, the other sector which have an important impact on the water resource, which are the agricultural, the industry, and the municipal sector. So the real problem is not only how much water hydrogen require, but where and when the water demand is added to some already stressed system. For what concerns the climate impacts, we also performed a comparative life cycle assessment across the case studies. So from life cycle point of view. And in the next slide, one very clear conclusion emerged. So if we are going to evaluate the impact on the climate change, the climate impacts are driven mainly by the electricity supply configuration. Projects that are supplied by carbon-intensive electricity systems show, of course, significantly higher greenhouse gas emission than projects when we have renewable electricity. Water treatment system and electrolyzer material contribute much less to the climate change impact. For what concern the water use impacts, let's say the results that we achieve tell us a slightly more complex story, because if we go to the next slide, we can see that the electricity supply again plays a critical role, but at the same time the source water selection and the local hydrological context significantly influence overall the performance. So a project that is located in a water abundant region may have a different profile and a different impact compared with an otherwise identical project in a water scarce basin. So again, this confirms that the water sustainability is really site dependent and local dependent. And for what concerns the socio-economic impact, our assessment that you can see in the next slide show that growing employment impacts across the analyzed macro region up to 2050, with a particular strong growth in the North Africa and Mediterranean countries, but also a significant increase in the Southeastern Europe. So this study has the aim also to identify the broader economical benefits linked to the investment, to the industrial development, and the value chain expansion. So this means that sustainable hydrogen deployment should not be only as an environmental challenge, but also an opportunity for regional development and industrial competitiveness and the job creation. So for what concerns the main recommendation, not only at case studies level, as introduced to you by Gianluca before, if you can go to the next slide. So the main recommendation, we have several actually practical recommendations that emerge during the study. First of all, let's say, from moving from a regional screening to basin level and site level assessment before final investment decision is really important for the local hydrological condition. And more the integrated water management, it's important for the water management overall, and water should be managed from the start of the project as well, as has been, let's say, see also from the stakeholder perspective that we see before. Then, for what concerns the alternative water sources, of course, seawater may be appropriate in coastal region. Treated wastewater can support circular water management strategies when the infrastructure is available, but its variation in quality still poses several concerns. And in general, water management strategy must be adapted to local hydrology, seasonal variability, and project characteristics. So the key message is that water availability and water resource is really important for hydrogen and mainly need to, let's say, considered also towards the water request of all the other sectors that are present in the same context and in the same ecosystem where the hydrogen production plant will be installed. So to conclude this session and the overall study results, so our results demonstrate that renewable hydrogen can be compatible with sustainable water use, but this compatibility is not automatic and it depends on planning decision and policy decision. We will see it later in the panel session as well. So I would like to close this session. Thank you for the attention for this first presentation. And we have covered, even if, okay, sorry, I already, let's say, go through this conclusion briefly now. So I would like to go directly to the question and answer because we have covered a significant amount of aspect today. So we are a little bit behind of the schedule. So I will maybe go through few questions that has been included in the question and answer chat, and then we can move to the panel discussion. So I see a question that maybe Gianluca, you could answer. What were the main reasons behind the selection of the 5 case studies?
Yes, I already answered in the chat, but anyway, the case studies were selected to, as I wrote here, to capture a wide range of climatic, hydrological, and operational conditions across Europe. And the idea, let's say that the objective was not to cover every European context, but to represent the main contributions, the main combination in terms of water stress, water use efficiency, renewable hydrogen, renewable energy potential, and the hydrogen market maturity. So the 5 case studies in this sense span from highly vulnerable context, for example, Mallorca and Greece, to very robust ones like, for example, Slovakia, with intermediate situations represented by France and Croatia.
Thank you, Gianluca. And I see also a comment that it's good to see treated wastewater that is mentioned again as an alternative water source for electrolysis. So yes, in some specific context, also treated wastewater, it's a very good alternative water resource. And a lot of research is doing also on this aspect, also thanks to the Clean Hydrogen Partnership opportunity to evaluate and to study from a technology point of view the use of low quality water as a water source for the electrolyzer. And this will be discussed a little bit more in detail during the panel discussion. on which I would like to go directly. So the objective of the panel discussion and in the next session is to connect the findings of the study that we had with the policy priority, the industrial perspective, and the future research direction. So first of all, let me present Alessio Tarantini, the Innovation Proposal and Project Management Executive Director in RINA, which will moderate the panel session. And I'm delighted to present briefly you our panelists. The first one will be Luca Feola, which was the project officer from the Clean Hydrogen Partnership that support us during these studies and will provide the perspective of the European hydrogen innovation ecosystem. We will have Marco Vavassori, Sales Manager, Hydrogen Business Unit from De Nora. I'm briefly present also Julie Mogin from SEA, which is the Deputy Director for Hydrogen Technology as SEA Litten. The four panelists will be Marco Serafini, Scientific Project Officer from the Joint Research Center, that will help us to connect this finding with the European evidence-based policymaking. And finally, we have Arno van den Bos, an analyst from IRENA, who will bring to us an international perspective. So I'm delighted to leave the floor to Alessio to moderate the panel session.
Thank you, Alessandra, and thanks everyone for joining this panel session. Really interesting to hear about the study that we performed with our partners for Luca, basically, because we developed a number of activities, and during the previous session you helped us to better understand in detail what has been done in this specific project. And I jump directly to the first question in the interest of time to Luca, because since Luca represents the Clean Hydrogen Partnership, I would like to understand more the context of where this study is located and what are the other activities that the program is going to fund, and what are your priorities from a technical and strategic perspective. Luca, if you want to help us to better understand what are your areas of interest.
Yes, thank you, Alessio, and good morning, everyone. Indeed, if we look at, we'll try to draft an answer about where the study fits and also how it can contribute to the higher scheme of the European Commission agenda, both on water and hydrogen. For what concerns our activity at the JU, today we address the entire supply chain of hydrogen. So we do research and innovation project on the entire supply chain. This goes from the hydrogen production to the storage and distribution of projects of hydrogen to the end users, which can be end users for transport or stationary applications. We have demonstration project of hydrogen valleys that also have contributed to the case studies within this study. And then transversal topics that we call it cross-cutting topics on RCS, safety, skills, and sustainability. Now, if we want to place the study in question on the water within these activities, perhaps we need to zoom out, and we need to look what we did in the last 17 years with all this variety of projects that we have, because historically one of the first data that developed as the more prominent within our program were the end users, because the technologies there were the one that developed faster, that they could demonstrate a positive business case. But then within the years, things have changed, and we started to shift our attention toward hydrogen production, both in terms of hydrogen production through electrolysis, but also hydrogen production through other means of production, such as biological hydrogen, for example. And the reason is quite simple, is because of the European agenda, with the initiatives such as the Green Deal, the hydrogen strategy, and the REPowerEU that has set some clear production targets for hydrogen in Europe by 2030, which can be translated with 40 gigawatt of electrolysis and 10 megatons of hydrogen by 2030. So this has provoked a needed shift of our program toward hydrogen production. And together with this shift, this also came with an attention toward the water agenda and the water directives, because we are well aware that there is a water framework directive which looks at the health of the water bodies, and the water resilience strategy that was published pretty much at the beginning of this study, which looks at the efficiency of use of water. So with this study, we tried to merge the two, and we tried to find an answer to both questions about how to scale up hydrogen in a sustainable manner. So these were the questions that we had in mind in 2024. But if we look then from what we can do, not only thanks to the study, but also from our point of view as an organization developing hydrogen project, it's clear that today we're looking also at solutions that are producing hydrogen through electrolysis in a more sustainable way. So either through direct seawater, which I think we already have 4 projects running, or by using direct wastewater, so industrial water, or water coming from non-treated water, which was a subject of the call of this year, which recently closed. So not only we are shifting toward hydrogen production, but we are shifting toward a sustainable hydrogen production through alternative form of electrolysis. So I think this study and our program go hand in hand, and we will keep working on both subjects. And I think today's study with the result is just a starting of activity. And I stop it here, Alessio.
No, thank you, Luca. Thank you. I think it is extremely important to stop a moment occasionally, make a step back, and really try to have a sort of helicopter view of the context where we work, because it is really important, and then deep dive on the areas of our own interest. Now I deep dive on one of the points that you also mentioned in your answer, and was also mentioned in the last 10 minutes many times, and it is the alternative water sources. From the study, we understood that feed water quality can significantly influence the water footprint. In this context, we already, let me say, mentioned many times that alternative water sources can play a role. And today we have Marco Vavassori from De Nora, to whom I ask, what do you think it can be done to act in this direction? I know you are developing an untreated seawater electrolyzer, and I ask you if you can help us to better understand your perspective in these regards and how your technology can play a role.
All right. Thank you, Alessio. Thank you all for the interesting presentation. Yes, here I'm joining the call as De Nora, and bringing our industrial perspective now, so on this specific subject. So the main message from today's study, of course, is that water should not be seen overall as a barrier to the hydrogen development, but one of the parameters. So from the very beginning, when designing a new project, that is my main takeaway, and of course, is something that we're noticing more and more into the request for quotation that we are reading in, or the new project development we are seeing. As we saw again, clearly all the study is showing that the local conditions are of course various, and of course the challenges are depending on them. So what is workable in one region is very different from what other regions may face. Here I would like first to focus on a couple of real examples that we experienced in the recent past through and thanks to our technology partner, ThyssenKrupp Nucera. So a good example to be brought to this stage, in my opinion, was to discuss a moment about the NEOM green hydrogen project. All of you may be aware of it. Is the largest project built at the moment and is in Saudi Arabia, and is currently under development between Nucera, ThyssenKrupp Nucera, and De Nora Technologies. So this is a massive project that is planned to produce up to 600 tons of green hydrogen every day, and it's going to be powered by a 4 gigawatt dedicated renewable energy systems from solar, from wind, and basically the level of water, the water income per day can be sized to a roughly 6,000 to 9,000 cubic meter of water needed every day. The 6 to 9 is, of course, depending not just on the processes, but on the overall operational losses that are all included. Of course, in a desert environment, this is quite a significant amount. Nevertheless, the whole project, as you may know, the NEOM project, dedicated a seawater desalination infrastructure, which is actually able to generate 3 or 4 times the water that is needed for this specific intake. So it's going to serve all the other infrastructure that NEOM is building on there. So again, water was considered from the beginning in the project design, as you may imagine, since the area was claiming for it, and this, of course, is something that will not appear to be one of the main constraints on the deployment of the overall project. But another interesting example that came up to my mind when I approached this conversation is, of course, Northern Europe. So you know that also here our partner ThyssenKrupp Nucera is closely working with Stigra Green Hydrogen Steel project based in Boden in Sweden. Here is another interesting case because the context is almost the opposite. So the project in this case is benefit from abundant renewable electricity, which is coming from the hydropower system, which is close by to the Lule River, which is a large river in the northern part of Sweden. And again, also in this case, the water availability was not a constraint. So when they decided where to locate all the plant, it was strictly related to the renewable availabilities, but also to the water availability. So in this case, 700 megawatt size of electrolysis capacity to produce roughly 100,000 tons of green hydrogen per year, fully satisfying the water demand with an infinitesimal percentage of what the Lule River is guaranteeing. So that is well managed for and looking at the local resources that were available. So opposite conditions, but these two cases, which are one of the two largest projects developed at the moment, are showing how both projects are working and are developing since the water strategy was embedded inside the overall broader strategy of these investments. So again, no one-size-fitting-all solution for the sustainable water management, but something to be adapted region by region. Just looking ahead, as you and Luca were correctly mentioning, we are not just stopping at the current status quo. We, as De Nora, are moving towards the evolution of the technology, especially in the water electrolysis systems. And through some European projects, we've been involved in, I would like to mention two, Animal and Asterisk are two European funded projects where De Nora actively worked and is working since they are still in progress with university industrial partners. And here we are focusing on the next generation AEM electrolysis systems. And in both cases, in one case, we are looking towards seawater use, direct use, and the other one is focused on other low grade, so to say, water streams. Both are targeting to reduce the dependence on fresh water. And on the other side, I would like also to mention it's not just a matter of freshwater access, but is all about the overall capex that water treatment may be saved, all the water desalination infrastructure may be saved outside the old project. So again, ultimately also the full bankability of a project may rely also on these activities. So it's not just purely based on the water, but on the overall bankability and ultimately on reaching the target, which is building new projects for green hydrogen along the world. So what is encouraging for Animal, just to mention, and then I will conclude, it is already demonstrating more than 2,000 operational hours using saline water. So the project is already ongoing and is showing some good results. Of course, further fine-tuning will be required, and is not a solution we will have on the market in the next few years, but first results are encouraging. And again, also asterisk is showing how it could be more imminent in terms of results, since here the approach is combining minimal seawater pretreatment, so limiting the pretreatment of the water to be used for direct hydrogen production. So all these initiatives are helping to expand the range of the sustainable option for the future hydrogen project deployment. So this is probably the most critical aspect that I want to highlight and stress with this occasion. So in conclusion, with selecting the right technologies and properly planning the projects, I would remark that yes, the outcome of the study is aligned with what we are perceiving also out there in the market. And let's say the key is not to look for the universal solution, but again to pick up the right solution for each territory and having the proper technology following each and every need upon the need. So thank you all for the attention, and of course available for Q&A also outside this webinar if that is needed.
Thank you, Marco. Thank you, Marco. Really interesting. It is always interesting to hear about real case studies. And I also really appreciated your considerations regarding the combination between sustainability and bankability. This means that using alternative water sources with the appropriate technologies could make the project more sustainable, but also maybe more bankable. And when both elements goes alongside, we have the success of the project. So thank you very much for your speech.
Pleasure.
Let's pass to the next speaker, who is Julie Mugin. Thank you again for being here. With you, I would like to touch base regarding the previous point already discussed also by Marco, to understand beyond the NORA's technology what is happening in the innovation sector and in general in the technology market. And I would also like to get your perspective on another point, because we mentioned that working on the quality of feed water is a lever to improve the water footprint. Another one that was already mentioned in the study is also the role of cooling water. Cooling water represents a major contributor to the water footprint. So I think that improving electrolyzers and also system efficiency could provide a benefit. And I would like to understand with you what actions we could do to address also this second kind of challenge. Thanks, Julie.
Thank you, Alessio. So I fully agree with what has been said before. I really think that we do not need to think in terms of replacing fresh water by a single alternative source. We really have to match available water resource with the appropriate hydrogen technologies while considering local environmental and economic conditions. So right now, we all know that the commercial electrolyzers, they need high purity water, because the impurities, they can affect performance, durability, and catalyst stability. So each time we want to use seawater or brackish water or treated wastewater, the treatment of that water remains an important part of the system. So that means for research, we have to follow different directions. First of all, we are developing the electrolyzers which are more resistant or tolerant to impurities through improved membranes, improved catalyst, and also the cell designs in order to avoid the clogging, for instance. And it can really reduce the purification requirements and in the end, the overall water efficiency. And then that has been presented also before by Marco. There are several projects targeting non-conventional water sources. Seawater, of course, is the most obvious because it's the most abundant, but it's also the most challenging in order to cope with the chlorine ions, corrosion, and competing reactions. Brackish water, I really think it's attractive options because it's available in many regions, and the burden of the desalination is less than seawater. And I also trust that treated wastewater is particularly relevant also because it is an already collected feedstock in some plants, which is often available near industrial sites. So I think it really makes sense in many, let's say, developed areas. So from that perspective, we can really work at the research level in order to have technologies that are more tolerant to this kind of type of water. And you mentioned in your question, Marco, that another aspect is also very important, is the cooling. And I have to say that from a research perspective, I have the impression that it's still often underestimated. So it has been presented during the brief overview of the studies, but clearly, while the consumption for the electrochemical reaction is only 9 liters of water per kilogram of hydrogen, the total withdrawal of water for the real hydrogen plant can be in the range of 15 to 44 liters per kilogram. So it means that the cooling is really a matter. Of course, it depends on the cooling strategy and the climate, but it's really a matter. And just to make it very, let's say, schematic, if we have 2 hydrogen plants with the same electrolysis technology, they can have very different water footprint depending how we manage the heat inside these electrolyzers. And the cooling solution can really make a big difference and sometimes be more prominent than the choice of the feed water. And from the R&D perspective, I really believe that we have to move from optimizing the electrolyzer alone, because we often think at the material, the membrane, the degradation, and so on, to optimizing the entire water hydrogen system that will include these more water efficient cooling technologies, reducing the water and energy losses at all the different steps, including the purification also, and improving the tolerance of the electrolyzer and the wide range of water quality. So I really think that this level system approach, in my view, is where research can make the greatest contribution in the coming years, because the remaining challenges are not only electrochemical, but they can also, they need also to involve the water treatment, integration, long-term reliability, environmental impacts, and economics. So to make it very short, moving from only material and pure electrolysis core developments to a system integrated approach. That's my final key message. Thank you.
Thank you, Julie. Thank you very much. Getting insights on where the research could, let me say, focus in addition to the main topics we already mentioned is really helpful from my perspective. Previously, I mentioned that sometimes it is appropriate to make a sort of step back to get the so-called helicopter view. And now I ask Marco Serafini from JRC to help us in this regards, because we touched various, let me say, deep dive topics, alternative water sources, quality of electrolyzers, how to improve water footprint through improvement in the cooling water. Now I want really to understand from the European standpoint how all those elements can be put together. In terms of policy perspective, I understand that in Europe currently the water consumption in hydrogen production is governed by the existing water legislation, and there is no, at the moment, hydrogen-specific rules. I would like to understand from you, Marco, if you can help us in understanding if it is appropriate, if it is required to integrate this policy framework with additional hydrogen-specific guidance.
Thank you, Alessio. Thank you for the question, and thanks for having me. Yeah, as we have seen from this report, the situation of water in Europe is pretty different. It's based on the presence of different basin or the different geography. And therefore, even the water directive that we have right now is it has some difficulties to cover the whole European territory, and is fragmented under a lot of daughters directive that cover the local situation. And I agree with what also Julie was mentioning, that it's necessary to improve the research, improve the technology, to detach from the use of fresh water for hydrogen technologies. But it's also true that this research can be translated in other technologies, and especially when we see emerging markets or expanding markets like, for example, the data center, we can see that the water use used by the hydrogen sector is still has a limited additional impact compared to these other markets. Therefore, I don't think it's necessary to form a policy that covers the whole EU, just specific for the hydrogen. But I do believe the local policy should be improved to cover holistically how the water is used locally. And I think I can conclude here.
No, thank you, Marco. Thank you, Marco. Yeah, I reframe it in terms of responsibility, no? Because what has been touched in various speeches today is that there is not a unique solution. It is needed really to understand in the specific location, not in the region only, but also in the specific location, what is not only the amount or availability of renewable energy sources, but also the level of stress in the water system. In some instances, maybe we can avoid excessive stress, just let me say for fun. In other regions, we have to pay more attention. So maybe local regulation could help, and not a generalized regulation is needed. I would like to make a step ahead, making again a step back, because so far we discussed about technologies. We made a first step back coming to the policy requirements and policy in Europe. Now we can make another step back, and we can pass to the global perspective. Today we have Arnaud from RINA, to whom I ask, since he has a very specific expertise in the global perspective, maybe he can help us to understand if there are outside Europe policymakers that approach this kind of problem in a different way, how they addressed the water dimension in hydrogen production. Did they provided or defined specific policies, or they have an approach similar to the one we are using in Europe? Arnaud, please.
Yes, thanks, Alessio, and good morning, everyone. I realize we are short on time. I'll try to keep it brief. But so RINA, we're the International Renewable Energy Agency with 170 member countries. So, of course, we promote renewables, but we also have looked extensively at hydrogen as an enabler of decarbonization of hard-to-abate sectors. And in that context, we've been publishing about this since 2018. We had a publication specifically about water for hydrogen production in 2023, together with Blue Risk. I'll paste the link here so everyone can read it in more detail. We have found similar findings as the study you just showed in terms of water consumption, also compared to, for example, the methane-based with carbon capture, so blue hydrogen. We even find that it often uses more water. So we often recommend governments don't necessarily shift towards that as a solution. That has also many other risks. In terms of dealing with water, of course, it has been mentioned, water security is not nice to have. You must have it, not only today, but at least over the next 15, 20 years at least available. So climate risks need to be taken into account. And of course, one risk is in the future, if water stress increases, that because the amount of added value that is maybe not created, but enabled by 1 liter or 1 kilo of water is relatively high compared to other uses of water, there's a risk that it might actually be prioritized, which might lead to a risk in terms of social acceptance, right, and license to operate. So I think it's been mentioned, water should be managed on the hydrographic basin level, right? Ideally, you would have policymakers planning for this. This happens in many countries. But of course, project developers should also take into account the risks. And sometimes, if the capacity is not there to do this properly, enablers like development banks can also play a role there, right? So they can also assess the risks. So of course, apart from early engagement with the environmental regulators and the water assessments, examples. So it's been mentioned. I think Marco mentioned it earlier. The NOAM project in Saudi Arabia that's building excess capacity. So some examples of that I've seen also in Egypt. There's a Suez Economic Zone where the government has promoted the deployment of public-private capacity to do desalination on a very large scale. It can speed up permitting. It allows companies to connect progressively as they develop their electrolysis capacity. And there's some interesting examples from countries that have lots of experience in mining sector. So Chile, which is both a big mining country, but also a large hydrogen producer, have taken over some of these practices of requiring or at least incentivizing companies to build excess capacity, either for water treatment or for desalination, right? So allowing water to become available for other uses, either for domestic or for industrial and agricultural uses. So that's a way of ensuring not only availability, but also social acceptance. And so shared capacity can become an anchor for attracting investments. So the investments for hydrogen can also be used for developing additional capacity there. And we're seeing indeed that the Gulf countries, of course, are planning to use exclusively seawater, and we see this in North Africa as well. So I mentioned Egypt. Morocco is another country that's making good progress. On a policy side, Mauritania, perhaps worth mentioning, although their capacity is not as far developed. And yes, I think generally speaking, there's lots of examples where we can learn from other sectors and where this is being applied. But I'll keep it maybe short for now. Or maybe one question maybe I have for the rest. So we haven't researched this in depth, but if anyone has experience with combining desalination with extraction of CO2, right? So either from the brine or during the process, because when you produce hydrogen, you often don't need just the hydrogen. You want to produce either methanol or carbon carrying molecules. And I think there could be a synergy there that hasn't really been explored enough. So maybe this is an invitation for people to look further into that. And I'd be interested in the results.
Thank you, Arno. Thank you. No, thank you to all the speakers. Let me just try to sum up a bit a few keywords that I reported in my notes lively. We understood, generally speaking, where the Clean Hydrogen Partnership is directed in terms of priorities, in terms of program. We understood that there are some levers, both for the short term, that could be the lever related to the alternative water sources and electrolyzers that are able to accept that kind of water quality. We have also the possibility to work on cooling water to get efficiency. This comes not only from the research and development context, but also from the practical projects where smart siting can really provide an added value. Obviously, trying to be respectful and responsible, balancing the choices depending on the specific conditions. And also thank you eventually to the last two speakers for your perspective regarding the policy, because it is really important really to put all the pieces together and understand what policymakers should do and try to provide our really, let me say, added value in these regards. I leave the stage to Alessandra to close the session, and thank you everyone for the attention and the speakers for your speech.
Thank you, Alessio. And I will be very brief. You well summarized the main insights and results of today's webinar. So also from my side, I would like to thank all the speakers, all the panelists, and of course the Clean Hydrogen Partnership to support us for this study. It was a very interesting year of results and discussion around the sustainable water use in the hydrogen production. So as today we demonstrate somehow that renewable hydrogen production and sustainable water management are not, let's say, competing objectives, and on the contrary, we can advance together and find a solution for hydrogen deployment in the future without compromise the water availability. So I just remind you that the webinar has been recorded, so you will find the registration on the Clean Hydrogen Partnership together with the slides that we presented today. So thank you again for joining us, and I will close the webinar here.
Thank you, everyone.
Thank you, everyone. Bye-bye.
Thank you.
Thank you, everyone.
Bye.
Bye.
Thank you. Bye.